In this session, let us discuss about armature reaction of alternator, original armature reaction, okay, in a rotating machine. Already the conclusions, whatever were there, okay, already we discussed in the name of transformer. The same conclusions we are going to get. Okay, so from this session, at the end of this session, I will tell you, means there is nothing to remember in this session. Okay, but in order to get a feel, like how torque is getting developed, we should know this. Okay, now let us think of alternator, rotor. Okay, and here let me think of conductor A is here, conductor A dash is here, and conductor B is here, conductor B dash is here, and conductor C is here, conductor C dash is here. Okay, now let us think of my rotor. N1 S1. Okay, why I have written N1 and S1? Because though harmonics will be there in the field flux, we tried our level best to reduce the harmonics in field flux, and we tried to reduce harmonics in induced voltage also by having pitch factor and distribution factor. Okay, now basically this harmonic torques, okay, harmonic torques will not be induced in synchronous at all. Okay, so the moment torques will not be there, automatically power will not be there. Okay, because without torque, mechanical power is nothing but torque multiplied by speed. Okay, when torque is zero, though you have some speed, net power transformation will not be there for harmonics. Okay, about this point you will get the clarity at the end of induction. For as of now, let us go ahead without harmonic component. So fundamental component, in the sense we are considering sinusoids only. Now in which direction we have to rotate? Okay, we have to rotate the rotor in this direction only. Okay, so we have to rotate the rotor in this direction only. Why? Because if first A phase come, after that B should come, after that C should come. Okay, so if I rotate the rotor in this direction, phase sequence is going to be ABC. Okay, now let us think of induced voltage. Induced voltage in the sense right hand. Okay, means we never used left hand till now. See, flux is going to be in this direction. Okay, from N pole flux is coming in this direction, and my field is rotating in this direction, means that with respect to field, conductor equivalently is rotating in this direction. Okay, so my middle finger is going to give you induced voltage. That induced voltage is dot here, cross here. Okay, these induced voltages are going to be maximum or not? Yes, they are maximum. Why? Because this conductor is influenced by maximum flux density. This conductor is influenced by maximum flux density. So here it is going to be maximum induced voltage. Maximum induced voltage. Okay, now under no load conditions it's happy, happily you can rotate. But once the load is connected, the moment load is connected, in the sense my alternator is able to deliver electrical form of power, means that it has to absorb mechanical form of power, means that torque should be there, that should be back torque should be there. Okay, now let me connect resistance load. Okay, so let me connect this to phase A, let me connect this to phase B, let me connect this to phase C. Then what will happen? Currents will flow. Okay, so basically here voltage and current should be in line. For example, if this is voltage, okay, my current also should be in line with it. Okay, so whenever voltage maxima happen, at the same time current maxima also will happen. Okay, so as of now voltage maxima is occurring here and here, so current maxima also should occur here. Okay, and we also know that from our RMF concepts. Okay, if you get any doubt, go back and watch the video of concepts of rotating magnetic field video, then automatically you will come to know, because of 3 time displaced currents flowing through 3 space displaced windings. Okay, my resultant MMF, one resultant MMF at a magnitude of 1.5 F max. Okay, that particular F maximum will be aligned with the phase axis in which maximum currents flow. Okay, so because of all three time displaced currents flowing through all three space displaced windings, one resultant MMF will be formed. That resultant MMF will be aligned with the phase axis in which maximum currents flow. Maximum currents are flowing here. Okay, now one more thing is why I considered induced voltage dot. Current is also dot, because we also know that from basic concepts of rotating machines, like in generator, voltage and current should be in the same direction. In the motor, current should go against to the induced voltage. Okay, so it means my resultant MMF is going to be cross here, dot here. So because of all three time displaced currents flowing through all three space displaced windings, one resultant MMF will be produced. That resultant MMF is now here in this direction. So this is going to be FAR. Okay, now where is my field MMF? Field MMF from here to here, this is going to be field MMF. Okay, because N pole field MMF is in this direction. Now we have field MMF, we have armature MMF. So interaction of these field MMF and armature MMF, one resultant will come. Now what is our primary thing in order to produce continuous electromagnetic torque? Okay, means two conditions, number of poles of stator and rotor should be same, and second condition is stator MMF and rotor MMF should be stationary in space okay, then only continuous electromagnetic torque can be developed. For example, if it is rotated by 120 degrees, if rotor pole is rotated by 120 degrees, as of now A is going to maximum, after 120 degrees B is going to maximum. Okay, now if B is carrying maximum after 120 degrees, B current is going to be maximum. When B current is maximum, my net resultant, because of all three phase winding currents flowing through all three space displaced windings, resultant MMF will be aligned with B. Okay, so if it is rotated by 120 degrees, it also will be rotated by 120 degrees or not? Yes. So stator MMF and rotor MMF are stationary with respect to each other, displaced by non-zero space displacement angle or not? Yes. Okay, so continuous electromagnetic torque is possible to have. Now let us think of resultant MMF. My resultant MMF, okay, so resultant MMF is going to be this. This is going to be resultant MMF. Okay, in this resultant MMF, with this resultant MMF, for example, if you sit here, my resultant flux is going like this, resultant MMF is going like this. If you sit in the air gap and see the stator, okay, so if you sit on the stator, flux is going into the stator. Okay, so what is my resultant? Is going to be as pole here. Okay, because you are sitting in the air gap and flux is going into the rotor, into the stator. So resultant is going to be S here, resultant is going to be N here, and resultant here. Okay, now where is the torque produced? See here, all of you focus here. N pole is here, S pole is here, N and S will be attracted, so torque will be in opposite direction or not? Yes. Okay, so in a generator, direction of rotation and torque developed should be opposite to each other or not? Yes. Okay, so that's what is happening. So my rotor, if you are trying to move in this direction, my opposite torque will come. Beyond opposite torque, I have to push from the prime mover side. So prime mover has to deliver mechanical power to the generator, and the generator absorb that mechanical power. It will be converting into electrical power, and it is it is being absorbed by resistors. Okay, now let us think of lagging. Once you understand lagging and leading, automatically you will come to know what is happening inside the machine. Okay, now let us think of A dash, B dash, C dash. Okay, now let us think of my poles. N pole, S pole. Okay, now if it is rotating in this direction, again induced voltages, if you see dot here, cross here, those induced voltages are maximum or not? Yes, those induced voltages are maximum, because my conductor is exactly under the center of the pole. So this is going to be maximum induced voltage. maximum induced voltages. Okay, now let us think of if load connected at no load conditions, happy, like you can happily rotate the rotor, but once the machine is loaded, torque should be back torque should come. For example, let me think of resistance and inductance. Resistance, inductance are connected to phase A here, phase B here, phase C here. Then voltages are there, so currents will be flowing through them or not? Yes, so currents will flow. Okay, now let us try to draw the voltage current relationships here. So here it is going to be, voltage is going to be like this. Okay, if you think of current, my current is going to be lagging behind. Okay, so it is displaced by theta. Okay, my current waveform is lagging behind voltage waveform by theta degrees. Now focus here, all of you, here compulsorily you have to focus. As of now, for example, see here, as of now my pole is here, A is having induced voltage of maximum. Okay, now for example, when maximum currents will come in A, means after some theta degrees. So as of now voltage is maximum, but in order to have current maximum in A dash, you have to wait for theta time. Means that my rotor by that time will go in this direction. Okay, so when the rotor is here, induced voltages are maximum here, and you have to wait for current maximum. So by that time rotor will occupy this position. So once the rotor is rotated by theta degrees, then currents will be maximum in A dash. So once the rotor is here, current will be maximum here. Okay, let me repeat it again. As of now poles are here, means that voltage is maximum here. In order to have current maximum here, you have to wait for some time theta. So by that time my pole will go like this. When my pole is like this, currents here will be maximum. When my pole is here, currents will be maximum here. Okay, so where my current maxima is coming? Here. Okay, so here we are going to get current maxima as of now. Current maxima, and here induced voltage are dot. So currents also should be dot because it's generated. Okay, now let us see my field MMF. If you see, my field MMF is FF. Field MMF is FF in this direction. Okay, what about armature MMF? Means my armature MMF created because of three-phase armature currents, time displaced currents flowing through three space displaced winding. One resultant MMF will come, that is at 1.5 F max. We discussed RMF concepts. That MMF will be aligned with the phase axis in which maximum currents flow. So cross here, dot here, my armature MMF is in this direction because armature MMF will be decided by current. Flux will be decided by current. So my armature MMF is going to be FAR. Now where is my resultant MMF? Now my resultant MMF is here. This is going to be resultant MMF. Okay, if my resultant MMF is here, like again you are sitting in the air gap, my MMF is going into the stator. So here it should be S pole, or flux should come from here to here. Flux direction is here to here. So you are sitting on the stator. N pole should come here, S pole should come here. So this is going to be S pole of the resultant, opposite N pole of resultant. Now this N and S will be attracted or not? N, yes, will be attracted. So torque will be in this direction. Again, my speed, direction of rotation and torque are in opposite direction or not? Yes, because that should be back torque should be generated because it is delivering some electrical form of power. Now, see, if you see here, what is happening here? Like because of armature MMF, net MMF here is going to be reduced or not? Yes. Demagnetizing armature reaction effects. Okay, so demagnetizing armature reaction effects are happening or not? Yes. Okay, but in what way we analyzed by using transformer? We did not know all these things, frankly. We remember, like this is pi field flux. Okay, induced voltage down is going to be generator, induced voltage up is going to be motor. So induced voltage here is going to be generator. Okay, like transformer secondary. and the transformer primary is going to be motor. Now with respect to this, if I have lagging current, with respect to this, if I have lagging current of IA, okay, so pi AR will come here, and pi AR result in MMF pi R. Okay, so do we need to know all these things? Not required, because we know transformer. If you know one machine properly, remaining all machines automatically fall in their respective places. Okay, so my resultant MMF is reduced or not? Yes. Resultant flux is reduced or not? Yes. So it's going to have demagnetizing armature reaction effect or not? Obviously. Okay, now if it is having demagnetization armature reaction effects, in order to maintain same terminal voltage, you have to increase the flux. Overexcited. Anyway, let us think of alternator at leading currents. This is going to be alternator. Same A dash, B dash, C dash. Okay, let me think of the pole structure again. Same N pole, S pole. Okay, and let me rotate in the same direction as usual. Okay, see here my induced voltage is going to be dot cross maximum voltages. Okay, let me think of my load. Let me connect this A, B, C. Okay, so if I have voltage waveform here, voltage waveform like this, my current waveform is leading. Okay, so now if you see here, as of now pole is here. Okay, as of now pole is here. As of now induced voltage are maximum. But what about maximum currents leading? In the sense, see here, means as of now voltages are maximum, but prior to that currents maximum already went. Okay, so see here, if the pole is here, okay, if the pole is like this, okay, if the pole is like this, here maximum voltages are happening. Okay, now when maximum currents happen here, already previously it's gone. So as of now maximum voltages are happening in A, but maximum currents are already gone, means that maximum currents would have gone through them, like when the pole is here. Okay, so when the pole is here, maximum currents are there here. When the pole is here, maximum currents will come here. Okay, as of now maximum voltages, now maximum currents are already gone previously. So when maximum currents would have happened here in A dash, when the pole is here, maximum currents, as of now maximum voltages. So maximum currents are happening here, now when the pole is here, maximum currents will come to here. Okay, maximum currents are coming here, so maximum currents are going to be here. Okay, if maximum currents are here, okay, means maximum currents are going to be dot here, cross here. Okay, now let us see how my field MMF is going to be. My field MMF is here, FF. Okay, my armature MMF cross dot, armature MMF is in this direction, so armature MMF is here, because my armature MMF as usual, armature MMF will be aligned with the phase axis in which maximum currents flow. Maximum currents are flowing here, so FR is here. Now let me think of FF plus FAR is going to be FR. Okay, so again same old story. If I sit here in the air gap, my flux is going inside, to the stator, so my resultant is going to be S pole here, my resultant is going to be N pole here. Okay, so N to S attraction is going to be in opposite direction torque. Okay, so again torque is going to be in opposite direction with respect to the direction of rotation or not? Yes. Okay, so means that whenever alternator is loaded, automatically torque will be, back torque will come. That particular torque will try to stop the rotor of the prime mover, and beyond that opposition my prime mover has to rotate the alternator such that it will absorb the mechanical power alternator. Okay, now let us come back. Let us analyze, like, let us mix time and space. Okay, let me come back here. In this, means field MMF is space displaced because it is rotating, and armature MMF is space. So my resultant MMF is space. Okay, now what is time? For example, armature MMF is here. MMF is here means that my resultant current should be, means N into I is nothing but MMF. So my resultant current should be in line with this. IA. Okay, armature current, and here current and voltage should be in line. Voltage. Okay, so see, my currents and voltages are always time displaced. Okay, now but FR, FF, FAR is going to be space displaced. Now because of this, like, induced voltage, internal induced voltage is EF. Okay, now coming to here, my field MMF, resultant MMF, armature MMF are space. Okay, so my FAR is here, MMF is here. MMF by resultant number of turns is going to give you current. IA should be in line, and here current should lag behind voltage. So with respect to current, my voltage should be leading. Internally induced voltage should be here. Okay, now coming to here, again, like, field MMF, resultant MMF, armature MMF, all are space. Okay, and here current should lead voltage. So current is leading because FAR and IAR should be in line. IA, with respect to IA, my internally induced voltage should be lagging, or with respect to internally induced voltage, current should be leading. Okay, now let us come back here to the first one. Okay, see, torque is going to be in opposite direction everywhere. Torque is going to be in opposite direction everywhere. See, for example, let me introduce. Okay, basically this particular concept only we are going to use in our synchronous machines, and stability and faults analysis also we are going to use same in parallel operation everywhere. Like, synchronizing power coefficients, everywhere we are going to use the same. Okay, see dear, for example, this is going to be field pole. This is going to be field pole, N pole. Now my field pole I am rotating in this direction. Field pole I am rotating in this direction. But my resultant pole, like, resultant pole is going to be S pole. Okay, so for example, S pole, N pole. S pole, N pole is rotating like this. Okay, now is it motor or generator? We cannot say. But for example, if resultant MMF is here, resultant S pole, this is going to be S pole, for example, resultant S pole is here and resultant N pole is here, and I am trying to rotate in the same direction. Okay, so resultant N pole is here, resultant S pole is here, and it is like this. Okay, or NS, anything, like, opposite. So if I am rotating in this direction, means that, like, if I keep it like this, if I rotate like this, torque will be, this is the N pole, this is the S pole, this is N pole, this is S pole, torque will be in opposite direction. Okay, so for example, how to maintain this place here, means we have to apply prime mover. Okay, so what I will do, prime mover will have force like this, and this pole will try to go back torque. So I'm going to maintain this. Okay, so prime mover is giving some power, though it is trying to go back, our prime mover will not allow it to go back, such that S pole is here, N pole is here, torque will be in this direction, and my rotation is in forward direction. Okay, so in that way we are going to analyze.